We will do examples from the book. We already learned from last time that the derivative of sine inverse x respect to x is 1 over square root of 1 minus x squared. The derivative of tangent inverse x respect to x is 1 over 1 plus x squared. And the derivative of secant inverse x respect to x is 1 over x times square root of x squared minus 1. So we will now apply what we learned here. Now, number 24. We have y equals to cosine inverse of sine inverse of t. Oh, to do this derivative, I need to know the derivative of cosine inverse. Let's develop that first. What is the derivative of cosine inverse of x respect to x? What do we do this? How do we do this? So let's start with let y equals to cosine inverse x, dy equals to cosine x. I'm sorry, what am I doing? Cosine y equals to x. So by implicit differentiation, the derivative of cosine y is sine y times y prime equals to 1. Y prime equals to 1 over sine y, which will be 1 over square root of, I'm sorry, I have a negative somewhere. This is negative here, so this is negative, this is negative. 1 over 1 minus cosine squared y, that's 1 over negative 1 over square root of 1 minus x squared. So going back to this question here, if y is cosine inverse of y, then the derivative will be negative 1 over square root of 1 minus sine inverse of t being square times the derivative of sine inverse t. Okay, which is equals to negative. Derivative of sine inverse t is 1 over, let me write the first part first. Square root of 1 minus the square of sine inverse t times 1 over square root of 1 minus t squared. Okay, that's for number 24. Do you have any question you would like me to do? Let me know, okay? I do examples here. Number 26. Gx equals to square root of x squared minus 1 times secant inverse x. So g prime x will be the derivative of square root of x squared minus 1 times secant inverse x plus square root of x squared minus 1 times the derivative of secant inverse x. This will be x over square root of x squared minus 1 times secant inverse x plus, can you verify that? Okay, the 2 cancels in the derivative of that square root. And then the derivative of secant inverse of x is 1 over x square root of x squared minus 1, which is 1 over x. So the final answer here will be x secant inverse x over square root of x squared minus 1 plus 1 over x. Number 32. Number 32, y equals to tangent inverse of x minus square root of 1 plus x squared. Let me ask you to try this. Find what is y prime. I'll give you maybe 2 or 3 minutes at least to get a good feeling about this. Okay. The derivative of tangent inverse of blah is 1 over 1 plus blah square times the derivative of blah. Then I need to simplify it. So y prime equals to 1 over 1 plus x squared minus 2x square root of 1 plus x squared plus 1 plus x squared times 1 minus x over square root of 1 plus x squared. Is that right? And then this will be this will be 1 over 2 times 1 plus x squared minus 2x square root of 1 plus x squared times square root of 1 plus x squared minus x over 1 plus x squared. Oops, sorry, with square root. Man, that's quite ugly, huh? Yeah, that's quite ugly. On the top, I don't think I can simplify further. Let me just leave it like that for now. At the bottom, I can factor the 2 and then 1 plus x squared bracket square root of 1 plus x squared minus 2. No, minus 1. Oh, no, minus x. Duh. See, because the 2 out, these two guys becomes this, right? So I have x left. See, I simplify that so much, then I get this is equal to 1 over 2 times 1 plus x squared. You may want me to, maybe I write what happened in between first. So on the top is okay, that's 1 plus square root of 1 plus x squared minus x. At the bottom, it becomes 2 1 plus x squared times square root of 1 plus x squared minus 2x times 1 plus x squared. I hope now you see the common factor, 2 times 1 plus x squared. Okay, and something cancels. That's for number 32. How about number 34? Number 34, y equals to tangent inverse of x over a plus natural log of square root of x minus a over x plus a. It will be nice if you can do tangent inverse of x over a fast. Let's do it aside because we see that quite often, such that if you can memorize that, that will be great. Let y equals to tangent inverse of x over a. We see this very often though. We see this very often. So the derivative of that will be 1 over 1 plus x over a squared, right? The derivative of tangent inverse blah is 1 over 1 plus blah squared times the derivative of blah. That is 1 over 1 plus x squared over a squared times 1 over a. Okay, that will give us, if I distribute the a on the denominator, I will get a plus x squared over a, right? Now multiply the top and the bottom by a, give me a over a squared plus x squared. Okay, this later on will be very helpful when we do the integral. So in other words, integral of a over a squared plus x squared dx is tangent inverse of x over a plus constant. Right, now divide by constant a, I get integral of 1 over a squared plus x squared dx is 1 over a tangent inverse of x over a plus another constant. Okay, but of course later on when we do the integration, we may do it other way. At least now then we get, let me rewrite this first. This is tangent inverse of x over a. Now the second part here, instead of doing the derivative from there, you can also see that as 1/2 natural log of x minus a minus 1/2 natural log of x plus a. You can also do it that way. Okay, so y prime equals to a over a squared plus x squared plus 1 over 2 times x minus a minus 1 over 2 times x plus a. Which, if I go on simplifying the last two terms, if I try to simplify the last two terms, I wonder if we can do it fast enough. You try to do it. Okay, you try to do it. But I think I will get a over, that will be a over x squared minus a squared. Is it right? I don't know. Question mark. Let's try to do it regular way. So I will redo this number 34, but I do it right away. So y equals to tangent inverse of x over a plus natural log of square root of x minus a over x plus a. So y prime here, this one we know, that's a over a squared plus x squared, plus the derivative of natural log of blah is 1 over blah times the derivative of this. See what happens if we don't simplify it first, then it will be a long journey. This will be square root of x plus a over x minus a times 1 over 2 times square root of x minus a over x plus a times the derivative of x minus a over x plus a. Then this is equal to x minus a, yeah, x plus a over x minus 2 times x minus a. Well, because this guy is actually the same to this guy, right? The reciprocal are the same. This, the reciprocal of this is the same to that. Okay, so the square root will cancel. Well, the derivative of this guy here will be x plus a squared at the bottom. On the top, we will have x plus a minus x minus a, which will be these guys cancel, one of them. This will be 2a. See, right? So I end up with 2a over 2 times x minus a x plus a. So finally, I will get a over a squared plus x squared plus a over x squared minus a squared. Okay, the same solution we have above. But what happened is then this method is a lot harder to do because we didn't simplify the natural log first. Okay, it'll be nicer if you can simplify that first. You see, it becomes a lot easier. Okay, now that's for this part. How about antiderivative or the integral? More or less, we need to memorize. So integral of 1 over square root of 1 minus x squared dx is sine inverse x plus constant. Well, because the derivative of sine inverse x is 1 over the square root of 1 minus x squared. So we basically just look at that backward. Integral of 1 over 1 plus x squared dx is tangent inverse of x plus constant. And then integral of 1 over x times square root of x squared minus 1 dx is secant inverse of x plus constant. Memorize this. We need to memorize this. So number 60. Number 60, integral from 1/2 to 1 over radical 2 of 4 over 1 square root of 1 minus x squared dx. Well, you can move the 4 to the front, right? You don't need to write this down if that's clear for you. But this is 4 times what? Sine inverse of x from 1/2 to 1 over radical 2. This is 4 times sine inverse of 1 over radical 2 minus sine inverse of 1/2. Now, what is sine inverse of 1 over radical 2? Pi over 4, right? What is sine inverse of 1/2? 30 degrees, right? Pi over 6. It has to be in radian though. Okay, it has to be in radian. So you know what? I'm lazy. Let me just distribute that first. This is pi minus 2 pi over 3. That's pi over 3. Number 62. Integral from 0 to radical 3 over 4 of dx over 1 plus 16x squared. But this is the same to integral from 0 to radical 3 over 4 of dx over 1 plus 4x squared. All right? Substitution, let u equals to 4x. So du is 4dx. Therefore, the dx is du over 4. Not only that, if u equals to 4x, then the limit, the lower bound, once you do substitution of a definite integral, you need to change the limit of integration at the same time. Okay, so u0 will be 0, and u radical 3 over 4 will be radical 3. Then the integral then becomes from 0 to radical 3 of du over 4, 1 over 1 plus u squared. That will be 1/4 tangent inverse of u from 0 to radical 3. Tangent inverse of radical 3 is pi over 3, I believe. And tangent inverse of 0 is 0. That's for number 66. I mean, number 62. How about number 60? Let me ask you to try number 68. Number 68, you do it, please. Number 68, integral of e to the 2x over square root of 1 minus e to the 4x dx. You will let your u to be e to the 2x. Okay, maybe 2-3 minutes. Okay, let's see. So if u is substitute e to the 2x, then du will be 2e to the 2x dx. In other words, 1/2 du equals to e to the 2x dx. That's this part here, right? Okay, now then this becomes integral 1/2 du for the yellow part. And here I have 1 over square root of 1 minus u squared. So this is equals to 1/2 sine inverse of u plus constant, where my u is e to the 2x. Yeah, because it is an indefinite integral, then we need to add the constant, right? Okay. The next couple questions that I'm about to do here is for us to have a good feeling on how to do this in general. The first one, something we have done before, integral of 1 over a squared plus x squared dx. Now we have the result already. We have the result already somewhere here. We already have the result. But I want to show you another way to do this. I want to show you another way to do this. This will be, I will factor 1 over a squared out. That way I get something looks like this. Then that 1 over a squared going out, right? And inside I will have 1 plus x over a being squared dx. Then I do substitution. U equals to x over a such that du equals to 1 over a dx. In other words, I can replace dx by a du. 1/a² integral 1/1 plus u² a du. So a/a² is 1/a, right? Integral du/1 plus u², that's equals to 1/a tangent inverse of u plus constant. That will be 1/a tangent inverse of x/a plus constant. Okay, now I want you to memorize this because you will see in chapter 7 we have this integral a lot. X/a² plus x². We see this integral a lot. Okay. Why 1/a² comes outside the integral? Because 1/a² is constant. Yeah, this is a constant. The variable of integration is x. So I can pull this out. It's not under the influence of x, right? So I can pull that out. Okay. Another one, what happens if we have integral dx over square root of a² minus x²? Let me write it down. a² minus x². Now you will factor 1/a² out, the square root of a² out. So you get 1/a here, integral 1/square root of 1 minus x/a given square dx. You will see later on with some substitution, this will be 1/a times sine inverse of x/a plus constant. That's sine inverse x/a plus constant. Okay, so the integral of dx over square root of a² minus x² will be like that. Now, do not memorize it too much like that at this time. It will be too much effort if you try to memorize this integral. Practice the procedure in between. Practice the procedure in between. One of the homework I will assign you in future is to prove some formulas we get at the back of the book, at the cover of the book. Okay, that's what I will ask you to do. Now, I'm about to finish. I would have a couple more problems I would like to do from here, especially number 80. That number 80 is actually a very well-known question. Number 80 is a question that they asked at USC department final, as I remember. Okay, some note. This note will be very, very useful. Let integral of fx dx equals to fx plus constant. So capital Fx is the antiderivative of lowercase fx. Then integral of f ax plus b dx equals to 1 over a capital F of ax plus b plus constant. Otherwise, we will keep on doing substitution for a simple substitution, linear substitution. Okay, proof. Integral of f of ax plus b dx. We will do substitution, right? Let u equals to ax plus b. So du equals to a times dx. In other words, dx will be du over a. Then I go on, this integral becomes fu times, see, the u is ax plus b, right? And the dx is du over a. But this is 1 over a capital F u plus constant. That's 1 over a f times ax plus b plus constant. Now that's why if you know this rule, this idea here, then you can do this problem actually quite fast. Okay, because this 1 over a is for this, right? Okay, now the coefficient of this substitution here, okay, du equals to 1 over a dx, right? Now, so a du equals to dx. That's how you get this a here. So if you substitute this to be your u, it becomes the sine inverse of u. Okay? It becomes sine inverse of u. But we have extra a, coefficient a, which is the reciprocal of the coefficient of that x in the substitution. Okay, let's apply this the following. Suppose, for example, something we have known way in the past. What is the integral of cosine x dx? The integral of cosine x dx. If you don't know this, drop the class right away. This is sine x plus constant. Is that right? So, using that idea, can you do this integral fast? How about integral of cosine 4x dx? This will be 1 over 4 sine of 4x plus constant. Okay, so basically you treat this as your u, right? You treat that as your u. You treat that as your u. The variable of integration is x. Now you have extra 4 here. Okay, now the coefficient of that x will becomes the reciprocal. Now cosine of u, when you integrate it, becomes sine of u. Otherwise, you need to do substitution again, you know, right? Otherwise, you need to do substitution here and there again. Imagine if I try to confuse you with this. This one. This is a very common integral you have. Integral of e to the ax plus b dx. Trust me, most of you will say, oh, u equals to ax plus b. So du equals to blah, blah. And you're so happy that you get the answer. While after I tell you this, you say, oh, you know what? This is linear transformation of the original x, right? Okay, so the b will not change that. The b will not change that. So this will be 1 over a e to the ax plus b as constant. That's it. That's all. Okay, that's if you have x being replaced by ax. X being replaced by ax. Number 80. Number 80. Let fx equals to x arc tangent of 1 over x for x non-zero. You see it is undefined when x equals to 0, right? Okay, and we fill in the hole with 0 if x equals to 0. Part A, is fx continuous at x equals 0? How do we prove that? Continuity. What I will do is, well, f0 equals to 0, right? Second, I need to find the limit when x approaching 0 of fx. I need to find it out. And they will be continuous if 1 and 2 are equal. Limit x approaching 0 of x tangent inverse of 1 over x. How do we do this? How do we do this? Any idea? No L'Hopital rule. You cannot use L'Hopital rule. Well, at least because we have not learned L'Hopital rule. Anybody? This is actually calculus 1 though. This is not calculus 2. This is calculus 1. No clue? Squeeze it. For x not equals to 0, tangent inverse of 1 over x must be between negative pi over 2 to pi over 2. Must be between negative pi over 2 to pi over 2. Right? Pick any numbers. Pick any numbers, tangent inverse of whatever. As long as it's not undefined in there. Any number. And the result must be between pi over 2 and negative pi over 2. Right? As long as the denominator is not 0. Now then, so when I multiply by x on each side, this will be pi over 2x on the right hand side. This will be negative pi over 2x on the left hand side. Now apply the limit. Limit x approaching 0 of negative pi over 2x less than limit x approaching 0 of x tangent inverse of 1 over x, limit x approaching 0 of pi over 2x. To make it safe, let me use equal sign here. But the left hand side is 0, the right hand side also 0. So from there, by squeeze, we get limit x approaching 0 of x tangent inverse 1 over x is equals to 0. Step 3, f0 equals to limit of x approaching 0 of fx implies fx is continuous at x equals 0. Part B. Is fx differentiable at x equals 0? Is fx differentiable at x equals 0? It is continuous, right? So once the function is continuous, then the next step is it differentiable? Proof or solution. Then we try to differentiate that, but not using formulas, okay? Because we patch this, right? We patch this. We have patching here. Okay, we did the patching, so it's not appropriate for us to do just the derivative. I mean by formula. No, we can't. We actually can't do that. Okay, we can't do that. What we can do is using the definition. So f prime x at x equals to 0 equals to limit x approaching 0 of fx minus f0 over x minus 0. Okay, so this will be limit x approaching 0 of x tangent inverse of 1 over x minus f0 is 0 over x. Fast forward, this is limit x going to 0 of tangent inverse of 1 over x. And this is this limit does not exist. Why? Well, because if you approach that from the right-hand side, x approaching 0 from the right-hand side, that's the same to limit 1 over x going to infinity of tangent inverse of 1 over x, right? That is pi over 2. But if you approach that from the left-hand side, approaching 0 from the left-hand side, then 1 over x will go to negative infinity. Which will give us negative pi over 2. You see the left-hand limit and right-hand limit not equal. Right? The left-hand limit and right-hand limit not equal. Therefore, the limit does not exist. And furthermore, therefore, fx is not differentiable at x equals 0. Now, what's wrong with this argument? Like you do f prime x equals to, see, fx equals to x tangent inverse of 1 over x, 0. What's wrong if I just do the derivative? And I say, oh, this is tangent inverse of 1 over x plus x times the derivative of tangent inverse. That is 1 over x being squared times the derivative of 1 over x is negative 1 over x squared. Minus 1 over x times 1 plus 1 over x squared. And then you say, but f prime 0 is undefined. because when you plug in 0 here, it becomes undefined. What's wrong with this argument? Okay, you think about that a little bit. Okay, while we take a break, we come back at let's come back at 8:40. But I want you to think about this. I want you to think about why this argument is not a correct argument to show that fx is not differentiable at 0. Why you cannot do so. Okay, let's take a break. We come back at 8:40. So your suggested homework from here is will be 6.6b from number 23 to number 39. Number 43, 45 are good ones. Think about it. Of course, number 57 to number 71 is good. Do the odd ones. That's for 6.6b. .8. L'Hopital rule. Indeterminate form and L'Hopital rule. Indeterminate forms and L'Hopital rule. Okay, let me show you the homework again. Now, one of your friends asked, will we go over the homework? No, I will just write the solution and post it. I will just write the solution for the the take-home quiz, right? Okay, and then I will just post it. When I post it, I will post it under, what's that? I will post it under the assignment. So that's assignment here, right? Okay, so later on, I will edit this and I will post the solution right above it. I will post the solution right above that. Okay, so that's how I usually do the quiz. Okay, I will not go over that. If you have any question further than that, then come see me during my office hour. Okay. Oh, by the way, my office hour for you, I don't have time for office hour before and after class. Before your class, I have another class. And after your class, it's already more than 10 o'clock. I'm not supposed to do office hour after 10. What you can do is you email me and I will give you the link when to meet me during my office hour, which you can find in the syllabus. Now, in the syllabus, you see my office hour Monday, Wednesday, 3 to 4, okay? But I will open the Zoom during the time for my statistic class. So if you have questions, you send me an email, I give you the link to their class. on Tuesday, Thursday from 10 to 11. Okay, so if you have question, you want to see me during that office hour, send me an email. I'll give you the link for that class. And on Saturday, if you have question during this time, send me an email. I'll give you the link for my Saturday office hour. Okay. Let me go back to my notes. Are you done copying this? You can see these notes, this homework later on in the discussion, because I will convert this to PDF and I put it under our discussion of the day. Okay, L'Hopital in the terminate form and L'Hopital in the terminate form and L'Hopital. Okay, I will quote from page 470 in the box. That says the following: suppose fx and gx are differentiable. And g prime x is not equals to 0 on an interval I containing A. Except at A itself. Except possibly at A. Now, suppose that furthermore, suppose that limit x approaching A fx equals to 0 and limit x approaching A gx equals to 0, or limit x approaching A of fx is plus or minus infinity, and limit x approaching A of gx is plus minus infinity. So basically, limit x approaching A of fx over limit approaching A of gx will be, quote unquote, not equals to, but quote unquote, 0 over 0, or plus minus infinity over infinity. Now, we call this indeterminate form. Then, limit x approaching A of fx over gx is equals to limit x approaching A of the derivative over derivative. Now, we are not doing quotient rule here. We are not doing quotient rule. We are not doing quotient rule. Okay, we are doing the derivative of the numerator over the derivative of the denominator. Okay, the proof for this L'Hopital rule, the proof, I don't think our textbook actually provide the proof. Maybe they do. Maybe they do. But you can see the notes from our textbook about why this is true. I will just apply these rules. Okay, suppose, for example, I go to the textbook right away. Suppose, for example, question number 8. Limit x approaching 2 of x squared plus x minus 6 over x minus 2. Okay, using calculus 1, we did factoring. Limit x approaching 2 of x plus 3, x minus 2 over x minus 2. And because x approaching 2 but not equals to 2, then x minus 2 is not 0. Right? Because x minus 2 is not 0, I can cancel it. Then plug in x equals to 2. That's the method we use in calculus 1. Now, suppose I apply L'Hopital rule. But you need to check first though, when you plug in x equals to 2 on the numerator, what you get. If you plug in x equals to 2 on the numerator, you get 0. X equals to 2 at the denominator, you get 0. Okay? But do not say this is equals to 0 over 0. No, that's not true. You cannot say it that way. No. Okay? You put kind of like a superscript notation. Okay? Just to let us know that this is the case, indeterminate case. Okay? And then we apply L'Hopital rule. I usually use equal sign. And the top of that equal sign, I use LH. Why can you only use L'Hopital if the pun? I don't understand that. The pun, what is the pun? If the limit is 0 over 0, why can you only use L'Hopital if that? Because that's what L'Hopital rule say. If you have 3 over 0, then it's undefined. It's not indeterminate. Okay, let's take a look on this one. Limit x going to 0 of x over x. What is this equal to? When you plug it in right away, if you plug it in right away, you get 0 over 0. Right? When you plug in, when we replace x by 0 right away, you get 0 over 0. That's indeterminate. Right? Okay. Yeah, and then what you did before, because x is approaching 0 but not 0, so x over x is 1. Then that's equals to 1. Now, what L'Hopital rule says, besides doing it that way, you can also do it this way. You apply derivative on the top, derivative at the bottom. That's what L'Hopital rule says. Okay, that's what L'Hopital rule says. Now, let me go back. Somebody asks, wait, is 5 the answer? Yes. For this one, we are done. 5 is the answer. But if we apply L'Hopital rule, then I do derivative on the top. That will be 2x plus 1 over 1. Then I plug in 2. When I plug in 2, I get 5. Now the thing is, not all case it's factorable, but we may still able to find the result using L'Hopital rule. Why couldn't we use this method previously? Well, because this is the first time you learn it. 6.8, you cannot apply that to 6.6. Oh, well, if you allow that to do, can I ask you a question from calculus 3? That's not fair, right? That's not fair. So we are not supposed to use the argument from what we learn later for something that we learned right now. No, that's not fair. Okay. Yeah. And of course, in your test, when I ask you a limit question, you can just use L'Hopital rule because you learn it already right now, unless I specifically say do not use L'Hopital rule. Imagine this question number 8. Imagine this question number 8. If I ask this question number 8, I say that find the limit. Okay, 1 point if you use L'Hopital rule, 2 points if you don't use L'Hopital rule. You know, and no, L'Hopital rule actually very helpful. Okay, but I don't want you to rely on that too much. Okay, I don't want you will see later on why you don't want to rely on that too much though. Okay, it opens a Pandora door, a Pandora box where if you think that it's something make it easy, I'll be laughing at you. Just pick problems from the book and you will feel the pain. Let's say, for example, number 16, limit theta goes to pi over 2 of 1 minus sine theta over cosecant theta. When you plug in theta equals to pi over 2, you will get 1 over 1 on the top. Right? Now, how about when you plug in at the bottom? That will be 1, right? Cosecant theta is 1 over sine. Right? So if I plug this in, this will be 0 over 0. I'm sorry, 1 minus 1 over 1. This is 0. This is not indeterminate form. So make sure you check that. It has to be 0 over 0 or infinity over infinity. Number 20. Number 20. Limit x goes to infinity of natural log of square root of x over x squared. Now when I plug in the infinity to the top, I get infinity. I plug in infinity at the bottom, I also get infinity. That's indeterminate form. Now because of that, then I will do the derivative. But before I do the derivative, let me modify that a little bit. This is 1/2 natural log of x over x squared. Now then I apply L'Hopital rule, limit x goes to infinity of 1 over 2x over 2x. So the derivative on the top becomes like this. The derivative on the denominator becomes like this. Why do we need to emphasize we are using orbital? No. This notation LH here is my notation. You know, like if I don't write this notation, then somebody will ask me, Thomas, how do you get from here to here? Then I tell them orbital rule, right? So before you ask me that question, let me answer that first. So you see my note is actually pretty clear, huh? Now you don't have to though. I mean, in your work, you don't have to, but what I have found before is you get confused with your own omission of writing details. You don't write the details and you get confused yourself later on. Oh yeah, that's right, you know? That kind of situation happens a lot, right? Now then, go on further. This is, if I simplify, this is limit x approaching infinity of 1 over 4x squared, which is 0. Now you try some problems. You try number, I think number 24 is easy. But let me show you that you may need to do the L'Hopital rule a couple times. So limit u goes to infinity of e to the u over 10 big over u cubed. Notice that when I plug in infinity, it will give me infinity over infinity case, right? That's indeterminate form. So I apply L'Hopital rule, limit u goes to infinity of 1 over 10 e to the u over 10 over 3u squared. Let me fix it a little bit, make it look nicer. Limit u goes to infinity of e to the u over 10 over 30u squared. That's still infinity over infinity case. Then let me do another L'Hopital rule. That's 1 over 10 e to the u over 10 big over 60u. Simplify. E to the u over 10 over 600u. And apply. That's still infinity over infinity. I apply another L'Hopital rule, but make sure you check infinity over infinity there. Okay, make sure you check that, because in case you have a number over infinity, then you cannot do L'Hopital rule anymore. And this will be e to the u over 10 big over 600. This will be infinity. Okay, that's for number 24. You try number 28. Limit x going to 0 of x minus sine x over x minus tangent x. Okay, let me give you 2 minutes for this. When I plug that in, when I plug in x equals to 0, I get 0 over 0. So it is an indeterminate form. So I apply L'Hopital rule, limit x approaching 0 of 1 minus cosine x over 1 minus secant squared x. Now what? You can apply L'Hopital rule again, but be a bit careful not to rely on that too much, because you may end up keep on doing the derivative of something which, if you simplify, you may get it easier. So let's say in this case, when I plug in x equals to 0, I get 0 over 0 again. I do L'Hopital rule again. Then I get limit x approaching 0 of sine x over 2 secant squared x tangent x. Right, the derivative of secant squared x, oh, I have negative. Which, when you plug in x equals to 0, you will still have 0 over 0. Do you want to go on? And you see, this is a case in which if you don't simplify that, you will never get the answer. I think I will try to simplify it from here. So let me put a question mark. Are you sure? If you can simplify, simplify first. Like for example here, let me simplify this first. This is 1 minus cosine x, and the guy on the denominator is 1 minus 1 over cosine squared x. Right? Now multiply the top and the bottom by cosine squared x. Then I will get limit x going to 0 of cosine squared x times 1 minus cosine x over cosine squared x minus 1. Notice that I can factor the denominator. Canceling this will give us negative 1. So this is negative limit x going to 0 of cosine squared x over cosine x plus 1, which give me negative 1 over 2. Okay, so do not keep on thinking that, oh, if you still get indeterminate form, just apply L'Hopital rule right away. No, it's not a good idea. You see this example, right? You will forever doing that, and you will say, Thomas, you give a hard problem. No, you just never want to make it simple. You just don't want to make it simple. Think of it this way. You don't want me to give you a hard question, but you never want to simplify it. In other words, you don't want to make it simple. You don't want to make it easy, right? But you want me to give you easy questions. Strange, right? That's a bad argument. No. So you see from this example, if you can simplify a little bit, okay? And that's why we teach you algebra first before you learn calculus, because you need to know algebra to do calculus. Right? You see what happened if you don't know algebra, you just know calculus. If you just know calculus 2 without trigonometry, you are that neat in Thomas class. No, it's actually just common sense. If you can simplify, simplify. The thing is, I know plenty of you have that habit, as if you think your L'Hopital rule is silver bullet that can solve all your problem. Okay? When should we stop the use L'Hopital rule? Second or third time of use? We never know. We never know. I have seen a case in which I do the derivative, the L'Hopital rule 9 times. And there's no other way around. It's possible. Okay? So basically, once you do L'Hopital rule, Okay, ask yourself, can I simplify this? If not, then you apply L'Hopital rule again. Otherwise, to try to simplify. Okay. Is there a case where the L'Hopital rule does not stop and you can simplify it? With the problem in our book? No, there's no such case. It's either the L'Hopital rule will stop and you get the answer, or you simplify it and then you get the answer. Is it okay? Now, so far we have learned indeterminate form as, note, we call indeterminate form we know that as 0 over 0 or plus minus infinity over infinity. Now, we have more in the indeterminate form. The next indeterminate form is indeterminate product. The case of 0 times infinity. The case of 0 times infinity. But the idea will be if fg gives you 0 to times infinity case, then convert that to f over 1 over g or g over 1 over f. What do you mean, Thomas? What do you mean, Thomas? Let's take a look on the following example. It's actually a textbook example. Limit x going to 0 positive of x ln x. Now notice that when I plug in x equals to 0, when I plug in x equals to 0, I will get 0 for the first factor. I will get 0 for the first factor, negative infinity for the second factor. This will give me 0, right? But this, when x going to 0 from the right-hand side, will be negative infinity. Now, 0 times negative infinity is what? It's indeterminate, because we don't know, is it faster going to 0 or is it faster going to negative infinity? Or do they actually go in certain kind of similar rate such that it becomes ratio? Now, what then this tell us is modify that a little bit first. You can modify that to be natural log on the top and on the denominator 1 over x. Right? So you move this x to be on the reciprocal. 1 over x. Okay? Now then, when you plug in x approaching 0, you will get infinity on negative infinity on the top and negative infinity, and positive infinity at the bottom. You will get negative infinity on the top and infinity at the bottom. That's indeterminate form. Therefore, I will apply L'Hopital rule. Okay, I start applying L'Hopital rule once I have the quotient give me indeterminate form. So you start from here, massage that first, becomes indeterminate form that we have earlier, then you apply L'Hopital rule. So if I apply L'Hopital rule, that will give me limit x going to 0 positive. On the top, I get 1 over x. At the bottom, I get negative 1 over x squared. Simplify that first. That's negative x, right? Okay, let me slow down. That's negative x squared over x. That's equal to negative limit x going to 0 positive of x. That's 0. In our textbook, we may see that case in number 42. Number 42, we have limit x goes to infinity of square root of x e to the negative x over 2. You see, when I plug in x goes to infinity, this is infinity, right? This guy will give me infinity, but this guy will give me 0, right? That's indeterminate form. So let's massage this a little bit, make it into limit of ratio. Rewrite it into limit of ratio first. I will do it this way. Thomas, how do I know that this is how you do it? Well, try to do it another way. The question of Thomas, how do we know we should do it this way? It's a type of question you have a lot actually in algebra. But my answer to those kind of questions is like, okay, if you don't do it this way, what other way do you have? If you have other way, why don't you do it that way and then try? That's how you explore it. Okay, that's how you explore it. Anyway, then from here you see this is infinity over infinity. That's the indeterminate form we have. So I apply L'Hopital rule. Limit x goes to infinity of 1 over 2 square root of x over 1/2 e to the x over 2. Simplify. So I get 2 over 2 square root of x e to the x over 2. That's limit x goes to infinity of 1 over square root of x e to, e to the, that's right, e to the x over 2, which is 0. Okay, because that's 1 over infinity. Okay, I hope you see that I emphasize enough that once you do L'Hopital rule and simply simplify first. Otherwise, it's so messy to the point that you don't want to deal with that. That's for number 42. Let me ask you to try number 44 to have a good feeling on this. Limit x going to 0 positive of sine x ln x. Okay, let me give you 3 or 4 minutes. Are you allowed to differentiate the original function for L'Hopital, or do you have to use the manipulated one that gives 0 over 0? You need to use manipulated one in the determinate form, 0 over 0 or infinity over infinity. Then you can apply L'Hopital rule. Okay, because the starting point of L'Hopital rule, if we look back to the theory, the starting point of L'Hopital rule is this. This is the starting point. It starts from 0 over 0 or infinity over infinity, right? So when we say apply L'Hopital rule, it means it has to be in this form or that form first. Okay, I hope I answered that question. So here I will modify this. I will make it limit x going to 0 positive of natural log of x over cosecant x. Then I apply L'Hopital rule. That will give me negative infinity over infinity. Negative infinity over infinity. I believe this is right. Cosecant. Yeah. So when I apply L'Hopital rule, I get limit x going to 0 positive of 1 over x big over derivative of cosecant is negative cosecant x cotangent x. Let's simplify. Let me take the negative to the middle here. 1 over x, I put the x at the bottom. Cosecant x at the bottom, I make it sine x on the top. Cotangent x at the bottom means cosine x at the bottom, sine x on the top. Okay, and this is equals to, do you want to apply L'Hopital rule again? Because when you plug in x equals to 0, you get 0 over 0. Is that what you want to do? It will never end though. You will see it will never end. Yeah, you will see it will never end if you keep on doing that. Well, you can try, go ahead. Okay, but if I were you, I will write it this way. This is sine x over cosine x times sine x over x. This is equal to negative limit x going to 0 positive of tangent x times limit x going to 0 positive of sine x over x. Now the thing is, from algebra, from calculus 1, we know this is equal to 1. We know this guy is equal to 1. This guy is equal to 0. So the limit is 0. Now, you can imagine if you actually go on with doing the L'Hopital rule again here, I really think it's going to be very painful. If you do L'Hopital rule again, that would be negative. Let me pull the negative out. Limit x going to 0 positive of 2 sine x cosine x over cosine x plus, actually minus x sine x, right? Okay, and then you plug in x equals to 0, what happens? Oh, not that bad. When you plug in x equals to 0, then you will get 0 over 1 minus 0, which is 0. Now let's see how we have progresses. Note. We start from indeterminate form of either 0 over 0 or plus minus infinity over infinity. Now then we say indeterminate product. That's when we have 0 times plus minus infinity, right? Now we have more cases of indeterminate, but we need to convert them to indeterminate form. The second one is the indeterminate difference. That's when we have infinity minus infinity. Okay, and then indeterminate power. That's the case of 0 to the 0 or 1 to the infinity, or there's one more case. Let's see, infinity to the 0. An example of indeterminate difference. An example of indeterminate difference. Let's say number 50. We have limit x going to 0 of cosecant x minus cotangent x. Now the idea is this. Every time we have indeterminate product, indeterminate difference, indeterminate power, we need to modify them first, manipulate them into indeterminate form. That's what we will do first. Once it is indeterminate form, then we can use L'Hopital rule. Now, so if we have this situation here, what do we do next? We need to write it as a quotient. Limit x approaching 0 of 1 over sine minus cosine over sine. So this will be cosine x over sine, like this, right? Then you will get 0 over 0 case. You get 0 over 0 case. So this is, you apply L'Hopital rule, you get limit x approaching 0 of sine x over cosine x, which is 0 over 1, that's 0. That's for number 50. Now you try think about number 52. Limit x approaching 0 of cotangent x minus 1 over x. Let me give you 3-4 minutes. I don't know the answer, but I think I will write it this way first. This is cosine x over sine x minus 1 over x. And then this is limit x going to 0 of x cosine x minus sine x over x sine x. Then from here, when I plug in x equals 0, I get 0 over 0, which is indeterminate form. So I apply L'Hopital rule. Wow, this will be nasty. That will be cosine x minus x sine x minus cosine x. Oh, not that bad. The numerator get cancelled. Something cancel on the numerator. On the denominator, actually, I don't need this parenthesis anymore. On the denominator, I have sine x plus x cosine x. Simplify a little bit. I get negative x sine x over sine x plus x cosine x. Uh-oh. What do you think I should do from here? I don't think I can simplify this further. Let's, I will do L'Hopital rule again because this is still 0 over 0. That 0 over 0 will give me, when I apply L'Hopital rule, I will get negative sine x. Oh, I'm sorry, it should be 0, not infinity. It should be 0 here. And then minus x cosine x big over cosine x plus cosine x minus x sine x. Ah, nice. So you see, when I plug in x equals to 0, I get 0 minus 0 over 1 plus 1 minus 0. Yeah, but here you see that you need to be quite disciplined with your product rule, right? Okay, you need to be quite disciplined with your product rule. Now, I have only approximately 5 minutes left. How about indeterminate power? I will do more on Wednesday. I give you an example right now, and I continue in future. You can try to do more also. Number 56. Number 56, we have limit x going to 0 positive of tangent 2x to the power of x. Now this will give us 0 to the 0 case. Now what's wrong with 0 to the 0? Why 0 to the 0 is called indeterminate? Why 0 over 0 is indeterminate? Here's the thing. any non-zero, any constant, non-zero constant to the power of 0 is 1. That's something we know. Yeah, that's something we know. That anything to the 0 is equals to 1 as long as C is not 0. Okay, on the other hand, 0 to positive exponent is 0. 0 to the negative exponent is undefined. Yeah, because 0 to the negative exponent is, let's say 0 to the negative 2 means 1 over 0 squared, right? That's undefined. Okay, now if these two ugly things put together, 0 to the 0, then will that be, but Thomas, if this guy here is very, very close to 0 but not 0, if this is very close to 0 but not 0, to the power of exactly 0, that's 1, right? Okay, it's very close to 0 but not 0. That's 1. Let me rewrite it. Limit x going to 0 positive of x to the 0, this is equal to 1. Okay, that one is easy. But what happens if I change the position, x going to 0 positive of 0 to the x? What is this equal to? This is 0, right? Because x is positive, so this will be positive 0. I mean, well, what do you mean by positive 0? It's just 0. On the other hand, when we have limit x going to 0 negative of 0 to the x, this will be undefined, as we have said earlier. Then what happens if we have limit x approaching 0 positive of x to the x? Will that be equals to 1 or equals to 0? Right? Because if the exponent goes to 0 first, then the whole thing here will be 1. But if if the base goes to 0 first, then the whole thing will be 0. Now the thing is the base and exponent are both x's. So they are actually approaching 0 at the same rate. We cannot decide. Okay? That's why 0 to the 0 is an indeterminate form, and we therefore need to be taken with care. Okay, how do we work on this? Idea, we will start with solution. We'll start with let y equals to tangent to x to the x first. And then apply natural law. So you see the power now becomes product. Then the limit of x approaching 0 positive of ln y is equals to limit x approaching 0 positive of ln of tangent x ln tangent to x. Now the thing is on the left-hand side, we learn from calculus 1, limit of natural log is natural log of limit. Basically, limit of function equals to function of limit. So you will see this on the left-hand side, there will be natural log of limit x goes to in 0 positive of y equals to, then on the right-hand side, you massage that a little bit. Like that. And then we go further. Okay, we will continue on that on Wednesday. At least your suggested homework here will be, I'm almost done. I'm almost done, a bit more. Suggested homework from this 6-8 will be number 7 to number 53. Oh, that's 6.88. Okay, that's for today.